Hello, Physics 1. Welcome to part 1 of Tuesday's lecture, week 17. So, last time we left off, we were finally able to write out the angular momentum principle in the standard forms that we've seen for principles like the momentum principle and the energy principle. Of course, the energy principle depends on work, which is force times distance. Whereas both angular momentum and regular momentum are with respect to time. But we can see that we've got the update form where final angular momentum is equal to initial plus any torque applied over the length of time that torque was applied. That the change in angular momentum with respect to time, either in derivative form or the delta form, will give you the net torque. And then because it's a conserved quantity, you can also write it that the total angular momentum of a system, or the change in angular momentum of a system plus the change in angular momentum of the surroundings, will be 0. So they can exchange between each other, but they can't exchange anything they don't already have. You can't add angular momentum to the universe. Okay, so next up, now that we've reviewed that, we're going to review how the angular momentum principle and the momentum principle are related. And this does use calculus. So this is more for the 211 class. So if you recall the momentum principle, the change in momentum with respect to time is equal to the net force applied. And using the change in position with respect to time being equal to velocity and momentum being equal to gamma mv, we can also state that if you cross velocity with itself, that's equal to 0. So dp dt is equal to F net. Okay, so this is what we're going to be using. So one of them's a repeat. And if any of these aren't clear to you, you should prove them to yourself. Okay, so. And also we're going to use angular momentum. So R with respect, the vector from A to the point of force crossed with the net force is equal to torque net with respect to that same point. So we're using product rule, which is something you learn about in Calc 1. So angular momentum with respect to A is equal to R with respect to A cross P. So dL A dt is equal to d RA cross P also. So basically all we've done is take the time-based derivative on both sides, perfectly legal to do. This is equal to dR A dt cross P plus, using product rule, RA cross dP dt. And so this is equal to V crossed gamma mv plus RA cross dP dt. And we've already stated that V cross V, so these are just constants, they're just going along for the ride. This is equal to 0 plus RA cross dP dt. And moving on, this is just 0 plus RA dP dt. We've already defined is just the net force. And what we have is dLA dt is equal to the torque net with respect to A. Cool. So, if you were wondering if you needed proof for that, which you should always need proof for anything I write down in this class, there you have it. Okay, so now that we kind of understand and see how we can use the different principles that we've learned throughout this class in conjunction. So as I've said before, physics is a topic that builds. We're always building in this class, building on previous concepts. It's not a unit-based class, it's a building class. Both are very good types of classes to take, but they have different applications in different fields. So momentum change for a seesaw. Let's calculate angular momentum. Five seconds. Sorry. 0.5 seconds after release from rest. So what we're referring to is the problem we did in part 2's lecture on Monday with Esther and Piper on a seesaw. So released from rest. And we want to know, will it go clockwise or counterclockwise? Okay, so the net torque on that system, which we have previously calculated, here it is, minus 592.9 in Z is that. And the problem setup, just a quick reminder. So we have 2 people, 14 and 70 kilograms respectively, sitting 1.1 away from a pivot point. So that's the problem we're referring to. Okay, so the net torque is equal to 0 minus 592.9 newtons per meter. So final angular momentum is equal to initial angular momentum plus the net torque with respect to A over delta t. So we have been given delta t right here. So it starts off at rest, so this is going to be equal to 0 plus 0 minus 592.9 Newton times meters times 0.5 seconds. This is equal to 0 minus 296.5 kilogram meters squared over seconds. So it's in minus Z. So point our thumbs down. Oh my goodness, it's going clockwise. So going clockwise. So once again, using the right-hand rule. Okay, so we have learned 3 fundamental principles in this class. And so now that we finally have gotten to the last one, we should write all of them down. So this is the crux of the classical mechanics section of the introductory physics sequence. So next semester we move on and we study basically the very beginnings of electromagnetism. So 3 fundamental principles. Fundamental principles. So this, all of them relate a change in system to an interaction. So delta P is equal to F net. Delta T, that's the momentum principle. Delta E is equal to work plus Q. And delta angular momentum, delta LA, is equal to the torque net with respect to position A, delta T. All of these are conserved quantities. That's why they're fundamental. So sometimes we learn about things that are not fundamental. Like, for example, many of the formulas used in circuitry are not fundamental equations. They require very precise conditions in order to be applied. They're very useful equations, but they're not fundamental. So there is a difference between, I think equations of convenience is probably a little bit too glib to call them that way, but equations that are very specific and equations that always apply. These principles always apply. Any system from interactions between different galaxies within the universe, or interactions at the subatomic particle level. So even at the quark level, these would still hold true. Okay, so the change of momentum of a system plus the change in momentum from the surroundings is equal to 0. The change in energy of the system plus the change in energy from the surroundings is equal to 0. The change in angular momentum of a system plus the change in angular momentum from the surroundings is equal to 0. And there you have it. There is the crux of Physics 1 all written right here. I guess we're done. Except for we should really do some more examples with angular momentum. Okay, so let us do that. So, section 11.6 basically follows really closely with what we've seen before. So you can see the multi-particle derivation in there. It's very, very similar to what we did in chapter 3. And we've done it with the energy principle, that basically what you get in terms of a sum formation. So the extended system model. So I'm just going to skip it, but you should read it on your own. So first part, do on your own. Okay, so the angular momentum principle . So basically you need to sum all the little points together. So the change of total angular momentum with respect to position A over the change in time is equal to the net torque at A. And delta L total with respect to A is equal to the net torque with respect to A times delta T. So basically just add them up. And often choosing A to be the center of mass will make your life easier. So that's often the easiest path to go down solving one of these problems. Not always, but generally speaking. So we would have the change of angular momentum of the center of mass with respect to time is equal to the change with respect to time of RCM, CM crossed with P total, plus L rotational. And so if you choose A to be the center of mass, then it's just simply equal to the change of rotational angular momentum with respect to time. So if you recall, we talked about this in Monday's lecture. RCM CM is equal to the zero vector. Okay, so we can now write out angular momentum principle. So the change of, let me try that again. The change of rotational angular momentum with respect to time is equal to the net torque relative to the center of mass, and therefore the change of rotational angular momentum is equal to the net torque relative to the center of mass times delta T. So, very convenient way to solve these types of problems. All right, so let's solve some of these types of problems. Let's look at systems with zero torque. So think about this as the systems that we looked at in chapter 3 and 2, where we looked at systems that had a net force of 0. So these are situations where the angular momentum of a system does not change. So one thing to note, the shape and moment of inertia might change, but not angular momentum. There is no torque being applied. Not during the interaction time we are looking at. By the way, athletes use this to their advantage all the time. So, for example, if you have an ice skater and she has a leg out and she is spinning. So she's spinning if she wants to spin faster. So there's nothing there to really twist her. What she can do is she can bring her leg in and her arms in, and she will go faster. This is due to the conservation of angular momentum. So typically, what I often do at this point in the class is when I am not with child, I will demo this myself. If I am with child, I will take a volunteer to demo it. But if you can do this in your own house safely, make sure that you're safe. But if you have a chair that spins, you can start to spin, put your arms out, then pull your arms in, and you will start to spin faster. Be careful. I have seen people fall out of chairs doing this, but this is something you can easily prove to yourself. Or if you have a trampoline, you can take advantage of some of these things. But you don't have to take my word for it. You can demo this to yourself. All right, so, for those of you that always like to know about the surroundings, there is some torque from friction on the ice, but it's pretty negligible. but friction on ice, it's on axis and negligible. So all she is doing is, because angular momentum is conserved, if she changes the moment of inertia, therefore the resistance to rotation, she will go faster because it will have to compensate for that change in inertia in some way. Okay, so let me write that out. So she changed her shape. And therefore changed her moment of inertia. So I1 omega 1 is equal to I2 omega 2. And so this will get faster in that case. So omega 2 equal to I, moment of inertia 1, times angular speed 1 over moment of inertia 2. So that's what she's doing. But in all of this, L rotational does not change. The moment of inertia decreases, and the kinetic energy increases as a result. And you might ask, well, energy conservation, where does this increase come from? And that would be chemical energy from the skater. Excuse me. So this is similar to a high dive jump. So fun fact about me, I once fell off a high dive. Ouch. So when you have these people who do high dive jumps, they jump, they're going straight down, then they'll curl up into a ball, go fast, and then straighten out once again. And so what they're doing is they're changing their moment of inertia by changing their shape, taking advantage of the conservation of rotational angular momentum to really get a fast spin going on, and then straightening back out. Okay. Let's do an example. So a satellite with 4 low mass solar panels. So that is one way that they power satellites, is they put solar panels on them. So it's circular. Let's just draw the solar panels like that. And it's spinning. Omega I. And it has some radius r. And it's also traveling with some speed v. Okay. There's our satellite. Initially traveling to the right with speed v and rotating clockwise with omega initial. Okay, then something happens. A small meteor with high speed, V1, rips through the solar panel. And as a result, meteor has reduced V2 after interaction. Let's draw the interaction. Here's our meteor. Okay, so it hits at height h, and we can see the angle that it comes in at, theta. All right, so that's the interaction, and we want to calculate Vx and Vy of the center of mass and the final omega of the satellite. So we started off like this, just minding its own way, and then it got struck. By the way, fun fact, one of the issues with interstellar space travel, so that would be traveling to different stars, is if they could build a ship using solar panels that could go fast enough to get it there within a reasonable amount of time. So right now, if we were to go to Proxima Centauri, I forget how many tens of thousands of years that would take at present rocket speeds, but you're basically generations of people would have to live and die before you'd get there. But let's say you built a faster ship. Space is mostly empty, but there's a lot of micrometeors in space, so like little iron nuclei. And if you go fast enough, they're basically going to shred your ship. So that is a real problem to contend with. Okay, so little aside, little cool, in my opinion, aside, done. Let's calculate Vx and Vy of the center of mass and omega final. So when we do the solution, what do we know? Okay, so we have information related to the momentum principle and the angular momentum principle. Remember, these abbreviations are just mine. So really not much about the energy principle. So these are going to be the two we're going to use. All right, so our system, let's choose the satellite plus the meteor. That will make the torque 0. Nothing, and then this is a collision interaction. So remember, and collisions have the property that they take place over too short of a time for anything of the surroundings to be of importance. So nothing, again, short time. Too short to be interesting to the surroundings. All right, so the initial state just before collision, and the final state is just after. Okay, so let's start out with the momentum principle in X. So Px final is equal to Pxi initial, mvx plus m2 cosine theta is equal to mv plus m1 cosine theta. So Vx is equal to V, so we're solving for this, plus m over m. So little m is the mass of the meteor, big M is the mass of the satellite. So V1 minus V2 cosine theta. Okay, so X component is done. Let's move on to the Y component. Py final is equal to Py initial, mvy plus mv2 cosine 90 minus theta is equal to m1 v1 cosine 90 degrees minus theta. Vy is equal to m over big M, v1 minus v2 sine of theta. And this is all relating to this image here. Okay, so we found two things we're after. We've got the y component of velocity, we have the x component. So we found two unknowns. I didn't give you any numbers, so I'm just looking for expressions. All right, so let's look at the angular momentum principle with respect to the center of mass. It's going clockwise in minus z. So we have the moment of inertia, omega I plus h, mv1 sine 90 degrees minus theta is equal to I omega f plus h mv2 sine of 90 minus 0. I is equal to two-fifths mr squared because it is a sphere. And so omega final is equal to omega initial plus hm over 2/5 mr squared v1 minus v2 cosine theta. Clockwise and into the page. All right, I think that is a good place to stop. We'll pick up next time with more examples of zero torque.